Now that we know what a graph is, let's go ahead and take a look at a couple of different implementations of how we could actually represent a graph using some of the data structure concepts we've already seen. So we're going to look at three different options. The first one will be the edge list, and then we'll talk about an adjacency matrix representation and an adjacency list representation. So starting off, let's talk about the concept of an edge list. So an edge list is based on the definition of a graph. So if you remember, we kind of defined a graph G as being a collection or a set of vertices or nodes and a collection of edges. And remember earlier I said that when I say a set of vertices, what we're really talking about is the fact that the vertices are distinct and it may not literally use a set data structure to store them, but conceptually it's a set. You won't have two vertices that would be considered completely and utterly identical. Okay, so in order to look at an edge list, I'm going to go ahead and kind of roughly sketch out a prototype in Eclipse. So let's go over to Eclipse. Okay, so here I am in Eclipse. I've created a public class edge list, and I'm going to just kind of sketch out some details within this class. So I know I'm going to have a class that represents a vertex. So I'm actually nesting this inside of the edge list class. So you can do nested classes in Java. Sometimes this is useful. This is a case where it might actually be advantageous. Don't worry about the specifics. We could create this in a separate file. It's just kind of for ease of showing you all the pieces here. I'm putting everything in one file. So a vertex would have to have some instance variables. So in all my examples, I've had some sort of a label on my vertex. There may be other data. So for example, in my power system example, each of the individual vertices was either a generator or a consumer of power. So the individual vertices also had data about how much power they were supplying or consuming. So that's just one example. Oftentimes vertices have other data besides just some sort of a label. And then of course we'd also have constructors and accessor methods and mutators, etc. Okay, so in addition to the vertices, we have to have the concept of an edge, so public class edge. Okay, so again, we would probably have some data that goes along with it, but as we talked about when we introduced graphs, the concept of an edge is really about the vertices that it connects. So we might have reference variables to, if it were a directed graph, a start vertex and a stop vertex, an end vertex, destination, however you want to call it. If this were an undirected graph, we'd probably still have two instance variables. It's just if we were dealing with an edge, we would need to check both of them because there wouldn't really be a clear definition of a start and an end, but we still have two distinct variables to represent the end points of the vertex. When we were trying to utilize them, we would not think of it as being directed. Okay, and then just like the vertex, there may be other associated data like weights if we're doing a weighted graph. And just like with the vertex, we'd also have constructors, accessors, and mutators. Okay, so the basic definition of a graph was just a collection of vertices and a collection of edges. So we could have a list in our graph of vertices. Of course, we'd actually have to initialize this in some way. We'd also have a list of edges. Okay, and in order to work with these, we'd have to have a constructor to construct our graph. We'd have to have accessors and mutators. So some of the things we might want to do are build a graph. So to build a graph, we'd have to add vertices. We'd also have to add edges between the vertices. So we'd have to add vertices before we could actually add the edges. And of course then at some point, once we've constructed our graph, we'll want to do some operations on it. We'll want to somehow process the graph. So that's one of the challenges here. A lot of times the operations that we want to do on graphs don't work very well with this approach of just using toList, with kind of using the literal definition of what a graph is. So I want to go back and look at a familiar example, the flight graph that we've looked at a couple of times already. So again, this is vertices that represent cities. The edges are weighted, and they indicate flights going from one city to another over some small time period. Okay, so what might we want to do with this graph? So that really drives what represents a good implementation or bad implementation. So we'll review implementations, we'll look at the concepts of time complexity, and we'll try and identify an implementation that leads us to the lowest overall time complexity. We'll also look at the concept of space complexity, which we haven't talked about much yet. Okay, so what do we typically want to do with graphs? There are kind of two major operations that are frequently done. They're certainly not the only things, but they're very, very common. So one of the questions that we often want to ask is, where can I go from here? So we can kind of think of this process of traversing through this graph as having some starting location, like St. Louis. And from St. Louis, we really want to know, where can I possibly go? So maybe I can go to Chicago. And then once I'm at Chicago, I want to know where I can go from Chicago. So it looks like I could go to Detroit directly. So I'll go ahead and go to Detroit. So that's one of the common questions we want to answer, and we want to have implementations that may be able to effectively allow us to go from a particular location and identify all of the outgoing arcs from that particular location. So if it's an undirected graph, all of the arcs that are connected to that location. If it's a directed graph, we want all of the outgoing arcs. We want to find all of the nodes that are adjacent. Okay, the second class of question we might want to answer is, can I get from here to there immediately? Are two things immediately adjacent? So in this particular graph, we may want to say, hey, is there a direct way to go from Chicago to Detroit? And it turns out there is. That's just a slightly different question. We're not looking at all of the outgoing arcs. We've got a very specific question with two vertices and asking whether those two vertices are connected. So these are two common operations. So let's think about how these two operations may work with our edge list implementation. Okay, so I want to work through an example to give some sense of how this is actually going to behave. So I've drawn out a little graph here, and I've put some labels on it. So it's got three vertices, A, B, and C, and it's got a total of three different edges, X, Y, and Z, and this happens to be an undirected graph. So I want to think a lot about how this graph data structure, this edge list, would actually work. In order to do that, I'm going to use some notation. So vertices, I'm going to draw with a little single box that will contain the label of the vertex. And edges, I'm going to draw with a little set of three boxes here that represent the two different outgoing links in the label. So again, I'm going to use the labels here, A, B, C, X, Y, and Z. And that'll be in the box for the vertex and in the center box of the three boxes for the edge. Okay, so we've got two different lists here. We've got our vertices, so I'm going to draw it as a linked list. So we'll have A, B, and C, and those will somehow be contained in nodes in a linked list. So I'm not going to worry about the details of how those are linked together. We've already covered those. So this is probably a doubly linked list, and it may have head and tail nodes. Okay, we'll also have a list that represents our edges. And we've got a total of three different edges here. I'm going to draw the nodes a little bit bigger because each node will have to contain this box with three different things in it. Okay, so we'll have our three different edges, X, Y, and Z, and each of these will be contained in nodes of a linked list, or some sort of a list. It could be an array-based list. I'm going to draw it as a linked list, and the nodes will include links to the appropriate vertices. So the edges, so it looks like X connects A and B, so it will have references to the A vertex and the B vertex. Y will connect B and C, so it'll have references to the B vertex and the C vertex. And Z connects A and C, so it'll have a reference to the A vertex and a reference to the C vertex. Okay, so our two major questions, where can I go from here and how can I get can I get from X to Y, are all about the edge list here. So if I want to know where I can go from A, I have to go through the edge list, and I have to look at each edge in the edge list and look at the two things that it connects up to. Is one of them A? And where is the other one? So in this case, one side is A, and it connects up to B. So I can go from A to B. Then I have to move on and look at the next edge. Neither of those two vertices are A, so that's not of interest to me at the moment. And then I have to go on to the next one. Oh, one of those two vertices is A, so I can also go from A to C. So if this were a directed graph, I'd also have to pay attention to which of these is which. If it's an undirected graph, I just have to check each of these to see if it's my starting location, and then I look at the other one to see what destination I can get to from my starting location. Okay, so our other question is, can I easily get from a particular node to another particular node? Again, we have to go through the entire edge list. We have to look at each edge. So if I'm trying to figure out whether I can go from A to C, I could start at this first node. One side is A. Is the other one C? Nope, it's B. Move on to the next one. Is one side A? Nope, neither of those is A. Move on to the next node. Is one of these connected to A? It is, and the other side is connected to C. So yes, I can go from A to C. Okay, so in both of those cases, we pretty much had to go through the entire edge list to answer either of our two questions. In a small graph like this, that isn't terribly burdensome, but this is an unusually small graph. In practical graphs, this is going to be problematic. So let's think about the estimated complexities for using this graph. So first of all, let's focus on our familiar concept here, time. Answering where can I go from here requires going through the entire edge list. So it's really dependent on the number of number of edges in the graph. So we can think of it as being theta of the number of edges. So it's exactly theta. We can't ever stop early in the list. The other question, can I get from here to there immediately, answering if two nodes are adjacent? Well, as soon as we find a place where they're adjacent, we might be able to stop. If it's a simple graph where we're guaranteed to only have one arc, so we can think of it as being big O of the number of edges. So let's talk about another concept that we haven't covered very much so far this semester, the concept of space utilization. And this is one of the things that we'll see is different between our three different implementations here. So basically our edge list implementation, we have to have a list of vertices and a list of edges. And so the total amount of space that we have is directly dependent on the number of edges plus the number of vertices. So our second approach is the adjacency matrix approach. So it's going to use a matrix for edges, and really by matrix we mean a 2D array. And if you remember, the idea of an array is that it has this random access property, so we can get to any particular element in constant time given its indices. Okay, so let's go ahead and take a look at this with our previous example, our simple small graph. Okay, so given our graph A, B, and C with the three edges x, y, and z, we can represent this by using a matrix of 3 columns and 3 rows. So 3 columns, 1 for each of our vertices, and 3 rows, also 1 for each of our vertices. So I'm going to label these A, B, and C, and also A, B, and C. And we can kind of think of the top as the start or the from, and so the columns are the from, and the individual rows are where it goes to. And any individual box in the array represents whether there happens to be an edge connecting these two vertices. So is there an edge from A to A? There's not. I'm going to leave that box empty. This could be a Boolean array of trues and falses. If it's a weighted matrix, these could be integers or floating point numbers representing the weights connecting things. So there is an edge from A to B. So again, this could be true or false. So from A to B, I am just going to fill in the name of the edge, I guess. And then there's also correspondingly the edge from B to A. So I'm going to go ahead and put an X in that box as well. We can go from B to C over link Y, or from C to B over link Y. We can go from A to C over link Z, so from A to C over Z. And of course we can do the reverse of that. We can go from C to A over Z. Okay, so with a simple graph, the individual boxes contain either the weight or details about the particular edge or arc between the two vertices. It would be possible to extend this to multi-graphs by having each individual box be a collection of edges. Also notice that in our undirected graph, this is symmetric about the diagonal. So if I've got something, if I kind of draw a diagonal line here, this is kind of a mirror image above and below. If this were a directed graph, it may not have this symmetry. The from and to would be more meaningful. Okay, so just like we did with the edge list, let's think about this adjacency matrix approach. Okay, so our adjacency matrix complexities, we've just kind of outlined. Where can I go from here requires us going through an entire row or an entire column for a particular vertex to see all of the places it's connected to. And we have to go through the entire row, so it's theta of the number of vertices. The other question, however, we do a little bit better at, can I get from here to there immediately, asking if two things are adjacent? That's, again, just looking up a value in an array, so we can do that in constant time. The total amount of space used is quite a bit different here, though. So the space is basically a square matrix of v by v, so it's number of vertices squared. Okay, so this does use a lot more space than our other implementation. If you've got a very large graph, it could use a profound amount of space. There are ways to represent sparse matrices sparsely, so there are ways to reduce the total amount of space used, but there's some trade-offs in terms of the amount of computation effort you have to do for certain operations, and it will kind of have an impact on our estimates of time complexity if it's not truly a 2D array with order 1 access time. That being said, so even though this uses more space, sometimes in weighted graphs there are some really great advantages to doing this. You can do some graph sorts of operations that overlap into linear algebra operations, and sometimes you can effectively express certain types of computations and certain types of graph operations mathematically. So the final implementation I want to look at is the adjacency list. And as the name kind of implies, lists are going to be used, and it's a list specifically of things that are adjacent to a particular node. So in ways, this is the most comparable to the actual graph drawings that we've been making. So just like the drawings, each vertex is going to have a distinct list of connections, of things that it's connected up to. Back to our familiar example one more time, our simple graph with 3 vertices and 3 edges. So just like before, with the edge list, we may want to have lists to represent both our edges and our vertices. Oftentimes we want to go through all the edges, so keeping edges in a list is handy. Okay, so just like before, I'm going to draw edge objects as having 3 distinct fields. So one of them will be the label, so my x, my y, and my z. And the other 2 fields will be references to the vertex object that they connect. Okay, now I'm going to draw my vertex objects, and these are going to be a little bit more complicated. So I'm going to draw them as kind of big boxes. Remember that all of these edges are in some sort of a collection, maybe a list, maybe a set or something. So we'll also have all of our vertices in some sort of a collection, again, maybe a list, maybe a set. So I'm going to go ahead and label these A, B, and C. Now what's more complicated about these is, in addition to their label and any other data about the vertex itself, each of these has a list or a collection itself of the edges that connect to that vertex. Okay, so let's go ahead and start connecting up our edge objects. So edge X has a reference to A and a reference to B. I'm going to ignore Y for now. This diagram is going to get a little bit cluttered. I'm only going to fill in part of the details to try and focus on the big picture here. So I'm going to mainly focus on vertex A and all of the connections that are relevant to vertex A. So that means that we also have to look at edge Z, which connects between A and C. So for the time being, I'm just going to ignore edge Y. Okay, vertex A itself has got some sort of a collection that will refer to the different edges. So I'm going to draw this as a linked list, although again it could be any sort of a collection. We have to think about whether we can access the collection in ways we want, but I'm going to go ahead and use kind of list nodes here. So A has a total of 2 edges it's connected to, X and Y. So its collection will somehow refer to, X and Z will somehow refer to those 2 nodes. Okay, so let's again think about our 2 different questions. Where can I go from here? So if I am at vertex A and I want to know where I can get to from vertex A, well, I can just iterate through this list and I say, oh, okay, there's this edge called X, one side is A, the other side is B. I can easily get to B from A. I can then move on to the next list item and say, okay, this also connects up to edge Z. One side of that is A, and the other side of it connects to vertex C. I can easily get to vertex C from vertex A. So this idea of figuring out where we can go from a particular node is really easy because we can focus on just the direct links from that node to all of the things that it's adjacent to. Okay. Our other question, can I get directly from node X to node Y? Well, if we know our start point, we can iterate through this list of edges and just look at the edges that might be relevant instead of all of the edges for the graph. So in a sense, it's a little bit better than our edge list at that second question, and it's a lot better at figuring out just the relevant edges from a particular vertex. Okay, let's talk a little bit about the adjacency list complexities. So first off with time, answering where can I go from here? So if we're at a particular vertex, we really might have a list that includes every edge. If the vertex is fully connected to everything in the graph, we may have a list of every possible edge. But most of our graphs are sparse. That's really unlikely in a sparse graph, and even if it does happen occasionally in a sparse graph, most of our nodes will be much better than that. And a lot of times, to answer this question, we need to know all outgoing edges. So this is about as precise as we can be. If a particular vertex is connected to every edge, then we want to look at every edge. This is really about the number of places we can go from a specific node, and this is a pretty good time complexity. It's hard to do much better than this to answer this particular question. Our other question, can I get from here to there immediately? Are 2 nodes adjacent? Well, again, we have to look at our starting place, our destination place, and we have to look at all of the vertices they're connected to by looking at their entire edge list. So again, in the worst case, we may have to go through all possible edges if a particular vertex is fully connected. But in reality, it's about the specific nodes. And in fact, if we're comparing 2 nodes, we can actually look at the node with the smaller edge list. Okay, what about space? Well, we have to have these 2 big lists, but basically we have each edge will occur in 3 different places, once in the edge list and once in the lists of each vertex that connects to it. So we basically have kind of a multiple of edge space compared to the original edge list. It's going to take more space, but it'll be directly proportional to the number of edges we have. And we also have these entries for each individual vertex. So the space is basically dependent on the number of edges and the number of vertices in our graph. And it's not a square like we saw with the adjacency matrix approach. Okay, it turns out that for many of the algorithms we're looking at in this course, the adjacency list is actually the better choice. So we'll mainly focus on this. So in your final assignment, you'll be working with a directed graph that's been implemented for you. Again, our graph will have a collection that represents the vertices and edges. It's implemented using hash sets, so a hash set of vertex objects and edge objects. There's a constructor that constructs those 2 sets. There's some methods to interact with them. So we'll want to be able to add a vertex. When we add a vertex, we'll also want to be able to add edges that connect together different vertices. We'll want to be able to determine the number of edges and vertices we have, and possibly iterate through the collections of edges and vertices. Okay, so this is entirely dependent on the hash set and the vertex and edge class. So let's take a quick look at the vertex, the edge class, and then the vertex class. So an edge is basically just made up of two vertices. So one of them is a from and the other is a to. Again, we're focusing on a directed graph here. So we leave the from and go to the to, and it only goes one direction. So the edge constructor is basically just about initializing those two references to the vertexes. So this is very much like the diagram that we just saw. It just omits the label of the individual edge. It's really all about the two things that the edge connects. So let's take a look at the vertex object. So the vertex object has a count. So this kind of keeps track of the total number of vertices in our graph. It also has two different lists. So this is a directed graph. So it's got a list of the successors, and it's also got a list of the predecessors. So each of these are lists of edges. Notice that it happens to be using an array list. It's also got methods that we need in order to work with vertices. We need to be able to construct a vertex, we need to be able to add edges to the vertex, and be able to iterate through the successors or predecessors depending on how we're traversing through our graph.